All right. So number 7, and someone can type into chat what the new groupings are and let them know. Okay, so I'm trying to determine absolute convergence, conditional convergence versus divergence. But what I would tell you is there's only multiplication going on. And when you've got multiplication between different types of things, ratio test is what you want. And ratio test, if it works for converge, makes it absolutely convergent and you're done. So I would use ratio test on this problem. So you do limit as n approaches infinity. You'd plug in a k plus 1, plug in a k plus 1, and it's actually k approaching infinity, and then divide by the formula itself. Then that's going to leave an extra 2/3 in the numerator. And when solving the limit, the k plus 1 over k piece is heading to 1. And if that was the only thing, you would get inconclusive. But it's 1 times this extra 2/3. And that's the answer to the limit. 2/3 is less than 1. So we get converged by the ratio test. But ratio test automatically is absolutely convergent. Altogether. Okay, so real quick, the groupings are A and C are Monday and Wednesday. B and D are Tuesdays and Thursdays. Okay, number 9. Number 9, I see this little -1 to the n, and I'm thinking I might go with the alternating series test. But at the same time, I'm remembering that I'm trying to find absolute or conditional convergence. And if the alternating series test works on this, it's only going to say you need to do some more tests on top of that. Then I also want to zero in on what I'm looking at over here and really think about it. Let me point out where your variable is located: an exponent and a base. When your variable is in the exponent, it looks like a why can I not think of my words? An exponential function, either growth or decay. Then if you have n in the base, then it's more like a polynomial. But if you look at it a little bit more and think about it, that 1.1 to the n, that's 1.1. That's a number bigger than 1 to the power of n. That looks like it's exponential growth and not decay, which, you know, thrown in with a P series situation, that geometric series is taking over. I'm looking at something that is probably divergent, and I want to use the divergence test. So I'm going straight over to there. So I would do limit as n approaches infinity of just the formula. And that answer is definitely diverge. This is a does not exist limit. But if you're not sure, you can do the ratio test on it as well. And let me point out that if you, so this is the divergence test. And that gives us a diverge. And was that a hand? Yes.
So my question was, so I found that, and I saw like right away that it was going to fail AST because the limit was not going to be 0. And
yeah.
So this is a little tick in my throat.
Yeah.
But in the answer key, it says that they did the ratio test, and I was wondering why. Because wouldn't it be easier to do it like the way that we did it?
You can do it that way. I don't know if they necessarily provide all the possible options. I will say that it's not necessarily extraordinarily obvious that this limit does not exist. So if you're ever not quite sure whether that limit is what you think it is, it's better to go with a different test. So if I go forward with the ratio test, I'm going to be really sure of it. First of all, I've got these negative ones that just kill each other completely, and I'm absolute valuing is really it. Then I've got the 1.1 to the power of leaves me with one of them in the numerator. Then when I look at this ratio, that's providing a multiplication by 1 multiplied by an extra 1.1. So I get a very definitive answer to that limit that I can clearly state it's greater than 1 and feel much more secure in what I found. And I know I'm getting diverged by ratio test. It's just the way that I have the test for divergence, you have to be really sure of yourself in what that limit is creating. If you really see that you're actually having to think about it, and I didn't bring in L'Hopital, so I had to really think about what I was working with and what ratio that would create. So that's why the ratio test in a way is better. It's more blatant, obvious with the conclusion.
Awesome, thank you.
And yeah, exactly. The exponential growth in the numerator always grows faster than a polynomial in the denominator. And yeah, you can visualize it. So either way is fine. Okay, with number 11, I would definitely turn to ratio test as I'm taking a good look at that. When I think about it, it helps to think what's happening in this ratio before you get started. So I want to think about this a little bit. If n is heading to infinity, 1 divided by n is heading to 0. And then the denominator is heading to infinity. My goodness, this is heading to 0. And because everything's multiplication in there, this is probably going to be quickest if I use the ratio test to get to absolutely converge. So with the ratio test, I've got plug in n plus 1. Now, I can say, hey, these guys are just -1. I'm absolute valuing, so they're going to be gone. I can look at this duo and see that that's heading to 1. And then I need to figure out what this actually is. Because by exponent rules, the numerator is turning into e to the 1 over n plus 1 minus 1 over n. Now, if you wanted to be really sure of yourself as to what you're getting, you can do a let's find the common denominator game. And that means doot doot times n, doot 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 doot, n plus 1, n plus 1. So this becomes e to the power of common denominator, and then n minus 1. That's a negative exponent. So if I simplify, I've got limit as n approaches infinity. I've got the n cubed over n plus 1 cubed heading to 1. Then this is supposed to be for the numerator, but I'm going to put it in the denominator with the positive exponent. And then I can solve that limit. I'm going to erase this if that's all right, because as n heads to infinity, this ratio heads to 1. For this, denominator is heading to infinity, so fraction is heading to 0. So this is actually heading to 1 over e to the 0 power. Uh-oh. Oh, I just saw it. E to the 0 power is 1. I can't do ratio test. Dun, dun, dun! So that's out. Number 11 is harder than it first looked. So in that case, I'm trying to think of...
I think what the key did was they did a, it was like an alternating series mixed with like comparison. And they basically said that e to the 1 over n is always less than e. So then you basically have
excellent
a series that you can compare it to. And you can say, since it's less than the converging P series, then it also has to converge.
Excellent. Thank you so much. While you might start with alternating series test, I would avoid it because it may not, if this is absolutely convergent, the alternating series test was useless. So this is a situation where if you absolute value the formula, you force it to be positive. And if you decide that you're going to check that sigma for converge diverge, wait, you're correct. Let me go through this to help you out. So what I'm going to do is I'm going to see if the absolute value of this formula, which is this, if I put that into sigma and test that for converge diverge, then if I get converge, I've got absolutely converge and I'm done. If I have diverge, then I need to bring in an alternating series test with it. So let's check it out. If this is my sigma, I want to think if there's something I can compare it to, because I do realize that 1 over n cubed, if I were able to compare it to that or a multiple of that, I've got a converging P series. Now, we just looked at the fact that as n approaches infinity, e to the 1 over n is heading to e to the 0, which is 1. So then I want to think about, is that the largest it gets or is that the smallest it gets? So I'm thinking about if I plug in n equals 1, 2, 3, 4, 5, I'm going e to the 1, e to the 1/2, e to the 1/3, e to the 1/4. E is bigger than the square root of e. E is as large as it will get if I'm plugging in these numbers. But the smallest it can get is heading to 1. So what I would actually do is I would set up that 1 over n cubed will always be smaller. E to the, or just e over n cubed will be bigger or equal. With that inequality, I am able to do converge or diverge, whichever it happens to be. And so then if I think about 1 over n cubed, I know, wait, I just realized what I wrote there, that I failed to write what I meant to. I meant to put this in the middle of an inequality so that I can go either way. I know that 1 over n cubed will converge, multiplying by a constant will get converge. I need to be smaller than a converge. So I could go as far as writing this massive inequality, but faster than, all I really need to say is that, oh, and that should be an n. E to the 1 over n cubed is positive, and it's less than or equal to, actually just less than, but that's okay, e over n cubed. I want to compare it to e over n cubed, and that is a P series, P equals 3, converge. I've got the inequality the way I need it. I've stated basically that I'm dealing with positive terms. So all of this together with direct comparison test stated that that is being used. I've got converge, and it's absolutely converge. So when I look at, this is e to the 1 over n right here. I'm going to move over here and just write down e to the 1 over n. When I plug in n equals 1, actually let me do it, it is a series. Then I plug in 2, I plug in, keep doing the commas, plug in 3, I can't stop myself from doing the commas. If you write several of these out, you might see it a little bit better. These fractions are heading to 0. This is heading to e to the 0 power, which is 1. And the 1 over infinity is the fact that we're dealing with limit as n approaches infinity, looking at just this piece of the whole thing. It's not the whole thing, but it's just one piece. This is e to the 1 over infinity. 1 over infinity is 0. And hopefully that should get you there. Okay, now those were the problems you said you wanted to see from the section of absolute converge, conditional converge. So now let's talk about choosing tests. Yeah, okay. Now, I want to point out to you the tests that we have. Okay. Oh, I have these things highlighted. Period 1 had asked about some of these specifics and how many of them have these extras that you probably should say. With the there we go. With the comparison tests, they require positive terms. Both the series you have and the series you compare to have to have positive terms. For the integral test, it requires the function you're using to be continuous, positive, and decreasing. But other than that, everything else is just, does the test work? Can I use it? Now, let me talk to you about how to decide the direction to take. And this is what I'm going to tell you. If you notice addition or subtraction, you're most likely going to need a comparison test if you see addition, subtraction within your formula. If you see a -1 to the n, you might head to the alternating series test. If you see only multiplication, so if you see addition, you might go to a comparison test. But if you see a whole bunch of multiplication, ratio test deals with multiplication really well. And additionally, if you see a factorial, ratio test deals with factorial. Then if you look at what's left, you've got the nth term test for divergence, which you should always be a little bit on the, have your eye out for it. The person at the door that says, hey, if your formula isn't heading to 0, don't even bother asking, do I converge? You so diverge, it's ridiculous. Then we have geometric series and P series, which often we end up comparing to those. However, sometimes you run into a pure geometric or a pure P series where you just head right there. You know you have a pure geometric series if your n variable of sigma is only in an exponent. You have a P series if you're dealing with the only n that shows up is in a base and you aren't dealing with any addition of other terms or subtraction of other terms. Then there's harmonic, which you can pretty much recognize on sight, which could fall under P series as well. The only thing left, if you look at the fact that I've highlighted everything that you're expected to know on the AP exam, the only thing left here is, I should extra highlight, harmonic series, we talked about it. Integral test, last resort. A lot of times an integral test can be avoided through a comparison test. But sometimes when you try to figure out what it can compare to, it gets to the point of, oh my gosh, I'd rather integrate than try and figure out what in the world I want to compare this to. And you will reach those points. And then you just go forward with integral test. So that's the basics of how you might approach that. So here we go. We're going to look at these odd problems one at a time and discuss what test to use. I'll ask you if you want to see the details, and you can tell me in chat. Number 1, look at that addition. That screams comparison test because of that addition right there. And let me add on to that you should also notice n is in an exponent on one of the terms, n is in a base on another term. That pushes even farther that you've got to do a comparison test because it's a mixture of something that's a geometric series with something that's a P series or harmonic series. You know the geometric series is going to win. And was that a hand? Yes.
Oh, yeah. So I was going to ask, is that like a good rule of thumb to have if there's like a test where you know there's like one variable but then
yep.
Its own observations, it's a good rule of thumb to resort to that?
Yes.
Okay, thank you.
Absolutely. That is a very good rule of thumb. I want to throw out there, though, just because, especially because I see it right next to it. If you have an addition, but you see that -1 to the n, there's a better likelihood that you're going to want to go to alternating series test or the divergence test if it happens to take you there. So that -1 to the n thing, really, when that comes in, even addition says, you know, I've got some negative terms. I can't do comparison test if I've got negative terms. So no negative signs, then go to comparison test if you see addition or subtraction.
I have a quick question.
Yes.
So on the keys, it
yeah.
says like they do AST and they do convergent for like the absolute value of a function.
Mm-hmm.
So you're saying when you said earlier,
mm-hmm.
all we have to do is prove that the absolute value of it's convergent.
Yes.
And then we can, because I kept on thinking about that, but then the key kept showing the series also.
Yeah. No, you don't have to. And I get that that would definitely be really confusing to be reading. And yeah, I'm trying to find, actually, I've got the textbook ready. So let me grab a theorem. I just need to find it over here to show you and make you feel even more comfortable. I've almost found it. Okay, I am bringing the textbook over. Theorem 3 right there. If you find that you have absolutely convergent, it is automatically convergent. So honestly, I don't know why the textbook was going through that extra step, because it is not needed. If you can show absolutely convergent, you're done. You can say at that moment, flat out convergent. And that is important to clarify if the textbook was giving you those answers. I didn't realize they were doing that. And that's confusing. Okay. Then, so with number 1, we would do a comparison test. Do you need to see number 1 done? The work for it. And if not, then let's take a look at number 3. That -1 to the n points to alternating series test, but always before you go to alternating series test, look at the rest of it and think about as n approaches infinity. As n approaches infinity, that's heading to 1, not 0. That means throw this into the nth term test for divergence. It's going to eat it up. And all you're going to do is put the entire formula after limit as n approaches infinity. The answer to that limit is does not exist. And at that point, you have shown the nth term test for divergence. Is it okay to move on to number 5? Unless you tell me differently, I'm moving on to number 5. And I'll tell you that what I see is a whole bunch of multiplication. My variable n is in a base here, which would be P series like. Then I've got n here in an exponent, geometric series like, and then another one there. When I've got multiplication of a mixture, I am just going straight forward to ratio test, no questions asked. I'm just going straight there. So I'm going to, do you need me to show the ratio test on that one? For this problem, the ratio test will end up giving you an answer of 2/5, which is less than 1. That'll give you converge. Now, number 7. Number 7 is a tricky one. And I've got to say, at first glance, I'm not entirely sure whether I'm dealing with converge, diverge. And if I try to figure out who to compare it to, I still need to have that inequality going the direction I need it to go. Now, you might be thinking, hey, let's try comparing it to 1 over n. 1 over n diverges. But the question is, what inequality are you in? So if I look at 1 over n root natural log n, I am looking at this denominator makes this fraction bigger. No, wait, sorry. Gosh, I keep going backward. This is why I question whether I have mild dyslexia. Anyway, if it makes the bottom bigger, the fraction itself is smaller. There we go. If I'm smaller than a diverge, that doesn't mean anything. If I try to do a limit comparison test, I'm going to get infinity. I'm not going to get a nice finite real number out of that ratio of these two items. So unless I can think of something that will work, I'm kind of going with maybe I want to head to the integral test. So, and now let me say that every time I throw on a test, a problem that I intend to make everyone do integral test on, even if I can't figure out what the comparison test would work out to be, I swear I always have a few people in the class who find that comparison to avoid the integral test. So there almost always is a situation. But if you can't find it, you need to turn to integral test. So I'm going to change those n's to x's. And then I'm going to bring it over to an integral. And I believe that started with a 2. So this would be the improper integral that I am allowed to use, where the integral test is going to say both converge or both diverge. However, I should double check the function. And I'm dealing with numbers. Let me just say if I'm dealing with numbers 3 or larger, just to make our lives a bit easier. If I'm dealing with numbers 3 or larger, this is definitely positive. It is definitely heading to 0. Or sorry, that wasn't it. Decreasing. And it is continuous for that domain. So those are the things needed to go forward and say, if this integral converges, so does the sigma. If it diverges, so does the sigma. Now, at this point, what I want to do is change this into a limit, because this limit determines if that improper integral is converge or diverge. And you know what? Let me change that. I'm going to make that a b, and I'm going to go 3 to b, where b is approaching infinity. Then I need to figure out what the function is when I integrate this. And I'm going to look at it as an indefinite integral, so I don't have to sit there and worry about those limits. And I know that I don't need the plus c because I'm putting it back into a definite integral situation. So anytime a logarithm shows up, you need to make it the u. If you get lucky, u substitution is all you need. Try it first. You know that du dx is equal to 1 over x. And what I'm going to do is I'm going to start this process by isolating dx and just plugging it in right there, see what happens. So I'm going to isolate dx by multiplying it to the right, but also multiplying x over to the du. And then this becomes and let's take a look at what goes. Cancel, cancel. And then the only thing I have left with x in it is what I chose to be u, so this is going to work. I have 1 over root u du. That means I have u to the negative 1/2. And I add 1 to the exponent, multiply by reciprocal, and I'm not going to bother adding c, but I do need to bother plugging the u back in. So 1/2 exponent means square root. U is natural log x. That is the answer to the integral 2 times natural log of x. And now I'm trying to go back over to the limit. And 2 times root natural log x. Now I'm plugging in the b minus plugging in the 3. And you should see that this piece right here Infinity goes into a logarithm, it grows insanely slow, but it grows. Square root the insane slow growth, still super slow. So very, very, very slowly heading to infinity. This is a does not exist limit. Because that limit does not exist, the improper integral diverges. And you need to fill in the rest of the information. So let me just say real quick. And if that diverges, then my sigma of the same formula, oh, that was 1 over, wasn't it? Then the sigma of the same formula, which is what I began with, diverges by integral test. If you are in a free response situation, keep it safe. And it's starting at 2 or 3, whichever. Keep it safe. Write everything that you need to write. But this is why integral test is closer to a last resort. So, moving on. Trying to make it bigger. There we go. Number 9. Can everyone see ratio test? You've got multiplication. I have a warning for you, though. When you see negative exponents, rewrite them as positive exponents to avoid silly errors that you look back on after taking a test and go, oh my gosh, I know better than that. But yet we make mistakes when we take tests if we look at things the wrong way, even though we know better. So rewrite it without the negative exponent, and you are far less likely for that to happen. And I can do ratio test if you want me to show it. Otherwise, I'm moving on to looking at 11 and what to do. I will definitely do 15 in full. So with number 11, you should really see that right away and go, woo, AST, AST, come help me. And then take a moment to think, if I took that piece out, do I have something that is decreasing to 0? Yes. That means go for it, AST. So through the alternating series test, understand that you have to first state you are dealing with an alternating series. Say it in writing. Claim it. Then state what the absolute value of that formula is. So this absolute value, I'm just going to write it real quick. Now, you can get away with writing that decreases to 0. In multiple choice, though, you need to be ready to go with the formal way that it's written, with the plugging in the n+1 being less than the nth term, and the limit as n approaches infinity of that formula. I'm calling that a sub n, by the way, and that's 0. That's all you need to be able to say converges by alternating series test. How often does AP ask what type of convergence versus just... It's rare that you get asked for absolute or conditional convergence. Most of the time, you're going to look at just converge or diverge, converge or diverge, converge or diverge. You might, and I'm telling you from looking at several AP exams over time, you might run into one problem in the entire exam that deals with the conditionally versus absolute convergence. Minor chance that you'll run into 2 problems total. Most of what you're going to work with is just plain old converge diverge. With 13, does everyone see that is so screaming ratio test, it's not even funny? I don't know where that phrase comes from. that it's not even funny. Anyway, number 15, we've got to deal with that. I am going to actually grab that problem and I'm going to bring it over and just sit all the way through it. Come on. Oh dear. That is my 10-minute warning. Come on. Do what I want. All right. Now, do you see you've got a factorial? That screams ratio test. It still does. Also, there's a multiplication in the denominator. Multiplication screams ratio test too. So here's what you want to do. Set up the ratio test. And you're going to plug in the n+1. And then multiply by the nth formula. And what's going to come into play is an actual understanding of what this ... is meaning and what is expected from that ... You want to understand that this sets up a basic pattern that is expected to follow this pattern. And whatever n you plug in to get this term, you're plugging the next n into this formula to get whatever was going to be the next term. Also, what you want to understand is when you're plugging in n+1, you're actually looking at what would have been the next term. And you want to realize that every time you go up by one n, you're adding another number to be multiplied. So if you realize in that ... situation that with every n that goes up, one more item gets tagged onto the end, then you know that the factor right in front of this in that ... is the previous factor. So that means that you can see that this whole mess cancels with all of this all the way through to this term, leaving you with only that in the denominator. For the factorials, you are allowed to take a factorial and write down what is in front of it, and then go take that formula, subtract 1, what do I get? You can choose to put a factorial on it at that moment, or you can keep going, and I'm just going to keep going for the sake of making sure you're clear. The next one would be n-1. I can put a factorial on right now on that n-1, or I can keep going, subtract another one. Put on a factorial or keep going. And, whoops. And then once you decide to stop, put a factorial on it and call it a day. Now, when you see this sitting there on the bottom, you realize that you only want to take it that far and put a factorial on the end, on the last one that you have. Those will cancel. And now I'm going to clean this up to see what we are actually working with. We have limit as n approaches infinity. We have n+1 left over in the numerator. And in the denominator, I have a 3 times n+1 plus 2. And you know, you can multiply it out if you want, but you don't need to. This is what's left over when everything cancels. So what is the answer to this limit? you should see that it's 1/3. 1/3 is less than 1. That means converge by ratio test. And so you got to see a situation where a factorial in the numerator actually did create a converge, which is pretty crazy. But if you look at what you're multiplying down here, perhaps you see that it does run that possibility. So that's 15. Everyone good with 15? Because that one was the one that was probably the hardest one to deal with. And then had I done 17? Okay, I did 17 with you already. Am I correct? Or did I just happen to do it in another problem? Because I feel like I just did that problem. Oh, wait, it didn't have -1 to the n in it, did it? There we go. 17 has -1 to the n. So does 19. So when you're choosing a direction, before you go with alternating series tests, take a moment to ask, just in your head, what is the limit as n approaches infinity? That's a really lousy limit, but n approaching infinity of the formula itself. We just looked at the idea of this. If n heads to infinity, 1 over n heads to 0, 2 to the 0 is 1. Oh, man. AST, you're not useful. But this one, if you think about it, as n heads to infinity, logarithm grows infinitely slower than a root grows. And you're able to know that that is heading to 0. So for number 17, you're going to use the nth term test for divergence. And with that, you're going to say limit as n approaches infinity of the whole entire formula. Now, it does not exist because it's oscillating between 1 and -1. Your main thing is just you need to say this is a limit that does not exist. That's all you need. Diverge. Due to that nth term test for divergence. For number 19, you want to go to AST, alternating series test. Always acknowledge it is an alternating series. Then take the absolute value of the formula. I'm trying to do it too quickly. And then all you need is for it to decrease to 0. If it's free response, you can say decreases to 0, or you can show the actual full writing of the alternating series test and plug in n+1 and say that that is smaller than plugging in n, because each term will be smaller than its predecessor, showing decreasing. Limit as n approaches infinity of the formula that you got out of the absolute value is heading to 0. You can L'Hopital if you need to see that it is 0, but logarithms grow infinitely slower than roots grow. And so there you get converge by AST. Now, how much time do we have left in class? Or did I go over time already? We have 2 minutes.
2 minutes.
Excellent. Is there another problem you want to see from all the mess that we've been doing? Give me a problem and I'll do it. I see nothing. Anyone have another problem they'd really like to see? Because we've got the time. We're now down to 1 minute. Then perhaps I should say over the weekend, really look at these tests. Really look at these tests. You may want to make flashcards for these tests to make sure that you are memorizing them, because you need to know them. You need to know their name. Let me also say that I posted a revised calendar, and things have changed for sure. I'm going to stop the recording. Come on. Why won't it work for me? Come on, stop recording. Ah! I clicked